There's something deeply strange about time that almost nobody ever stops to think about. And I don't mean strange in the way that a philosophy professor with a tweed jacket and too much coffee would mean it. I mean strange in the way that should make you pull your car over, stare at the steering wheel, and seriously question whether anything you've ever assumed about reality is actually true. Here on Feynman's Path, we take the biggest, most uncomfortable questions in science and philosophy, and we crack them open not with jargon, not with equations scribbled on a chalkboard, but with pure, ruthless logic. And today, we're going after one of the oldest assumptions baked into the human experience, the assumption that time flows. Now, before you check out, I'm not talking about some mystical Eastern philosophy about living in the present moment. I'm not about to tell you to light a candle and meditate. This is a physics conversation. And by the end of it, the ordinary, boring act of checking your phone to see what time it is will feel like the strangest thing you've ever done. Because here's the thing. That little glowing clock on your screen, it's lying to you. Not because it's wrong about whether it's 2:47 inches the afternoon, but because the very concept it represents time as something that moves, something that carries you forward like a river carries a boat, turns out to be, at best, a profound misunderstanding of how the universe actually works, and at worst, a full-blown hallucination that your brain has been running non-stop since the moment you were born. Let's find out which one it is. So let's start where every great physics conversation starts, with what feels completely, unquestionably, embarrassingly obvious. You experience time. Every single second of every single day. Right now, as you're listening to my voice, something is happening, moments are arriving, and then they're leaving. There's a you from 5 seconds ago who just heard me say hallucination, and there's a you right now who's still processing it. And in about 30 seconds, there'll be a you who's either nodding along or already reaching for the skip button. This feels as real as anything has ever felt. More real than your mortgage, more real than your keys being somewhere in this house, but you have absolutely no idea where. The sense that time moves, that you are being carried forward through it, is so deeply embedded in human experience that it's shaped literally everything. Our languages, our religions, our entire concept of cause and effect, the way we grieve, the way we hope. We imagine ourselves on a ship, and the ship is always moving. Behind us, the past, all those moments that have already happened, that have gone dark, that are finished and done. Ahead of us, the future unknown, unwritten, full of terrifying possibility, and also, occasionally, the faint hope that things will get better. And here in the middle, this thin sliver of the present, the now the only place where anything actually happens, this fragile, constantly moving window that we call the moment I'm alive in. Beautiful, right? Poetic, even. There's a reason every song ever written is somehow about time, every great novel, every deathbed speech. Because this image, the river of time, the ship moving forward, the fleeting present, it speaks to something so fundamental to being human that questioning it feels almost rude. So let's be rude. Because here's where it starts to fall apart. And I mean really fall apart, in a way that you can't paper over with a nice metaphor about rivers. Ask yourself this question and take it seriously, because it sounds simple, but it's actually a grenade with the pin already pulled. What exactly is time doing between events? You're sitting in your kitchen this morning. The coffee maker starts gurgling, then it stops. The coffee is done. Some amount of time has passed. Fine. But now imagine, really try to picture this. Imagine that absolutely nothing in the universe changes. Not one single atom moves. Not one photon travels. Not one electron orbits its nucleus. Everything in existence is completely, perfectly, absolutely frozen. Does time still pass? How would you know? What would it even mean? If nothing changes, if there is zero difference between the state of the universe 1 second later versus 1 billion years later, what is the word later even referring to? What's the clock ticking against? Richard Feynman, the Nobel Prize-winning physicist who spent his whole career picking apart lazy assumptions like a surgeon pulling stitches, Feynman used to have this way of cornering his students with questions like this. He'd say something like, "You think you understand something? Great. Now explain it to me without using the word you're trying to explain." And if you try to do that with time, if you try to explain what time is without reference to change, without reference to movement, without reference to things happening, you very quickly discover that you're holding onto an empty box. Time, it turns out, might not be the stage on which events happen. It might just be our word for the fact that events happen at all. The scorecard, not the game. If you strip away every single thing that changes, every process, every motion, you don't have time passing in an empty universe. You might just have nothing, and nothing doesn't tick. This is the hidden crack in the foundation. We've been so sure that time is the container and events are what get poured into it. But what if it's completely the other way around? What if events are the container and time is just the label we slap on the jar? Okay, let's follow that thread, because it goes somewhere genuinely alarming. So, if time is tied to change, if there's no meaningful difference between 1 second has passed and 1 billion years have passed in a completely frozen universe, then here's a natural question that should be scratching at the back of your mind right now. Is time the same everywhere? You probably have a very clear intuition about this. Of course it is. Obviously it is. Time is time. A second is a second, whether you're standing in your living room, whether you're on the moon, whether you're somewhere in a distant galaxy that we haven't even named yet. The universe has one big clock, and everything is synchronized to it. That intuition is exactly what Isaac Newton built his entire physics on. Absolute time, universal time. Time as the grand backdrop of everything, marching forward at the same steady pace for every particle, every rock, every creature in existence. Tick, 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 the same tick for everyone, everywhere, always. And here's the thing about Newton, he wasn't stupid. He was arguably the most brilliant scientist who ever lived up to that point. His physics was so accurate that we used it to get to the moon. Literal astronauts, blasting off into space, navigating by Newton's equations. When you're building a bridge or calculating how long it takes a ball to fall or figuring out the trajectory of a baseball, Newtonian physics is not just good enough, it's essentially perfect. The hidden assumption Newton was making, though the one nobody thought to question for over 200 years, was this. The speed at which something is happening has no relationship to time itself. In other words, it doesn't matter how fast I'm moving. My watch ticks at the same rate as your watch. Always. Without exception. Period. Makes sense, right? If you're standing still and I sprint past you, my heart is beating faster? Sure. I'm burning more energy. But my wristwatch isn't suddenly going crazy. It's still ticking once per second. It's still reading the same time as yours. Speed doesn't mess with clocks. Except and hold on to something, yes it does. Let's do a thought experiment. And I want you to really picture this one, because it's the one that broke Newton. You're standing on a train platform. It's a warm day, maybe a Tuesday. The 4:15 Express roars past you, going let's say 100 miles an hour. On top of that train, your friend is standing there like a maniac, holding a tennis ball, and they wind up and throw it in the direction the train is moving at 30 miles an hour. How fast does that ball look to you, standing on the platform? Easy. 130 miles an hour. The train's speed plus the ball's speed. They add together. This is so intuitive that it barely deserves to be called physics. It's just common sense. Now, same situation, same platform, same train roaring past, but instead of a tennis ball, your friend on the roof is holding a flashlight. And they click it on, pointing it in the direction the train is moving. A beam of light shoots forward. How fast do you see that light moving? Your gut says, the speed of light, plus 100 miles an hour. Obviously. Same logic as the tennis ball. And your gut is spectacularly, magnificently wrong. Here's what actually happens, and this is not a thought experiment anymore. This has been measured with real instruments to enormous precision. You see that light traveling at exactly the speed of light, not 1 mile per hour faster, not 1 mile per hour slower. Precisely, identically, the same speed of light as if the train were standing still. The speed of light in a vacuum, roughly 186,000 miles per second, is not just fast, it's constant. It's the same for every single observer in the universe, regardless of how fast they're moving, regardless of which direction they're going. There are no exceptions, there are no workarounds. It's the one thing in this entire cosmic carnival that never, ever changes. And now take a moment with this. Because it's important, ask yourself what that means. Speed is not magic. Speed is just a ratio. Distance divided by time. How far you've gone divided by how long it took. That's it. Those are the only two ingredients in the recipe. If the speed of light is always the same, if you and I both see that flashlight beam traveling at exactly 186,000 miles per second, even though you're standing still and I'm hurtling past you at half the speed of sound, then something has to give. You can't just declare that the answer to the division problem is always the same if the numerator keeps changing, unless you're also changing the denominator, unless time itself is changing. And that is exactly what happens. When you move faster through space, time, your personal, private, biological, experiential time slows down. Not by a lot at the speeds we normally live at. The effect is so tiny at highway speeds that it would take the most sensitive atomic clock on Earth to measure it. But it's real. It's not a rounding error. It's not a measurement artifact. It is a genuine, verified, repeatable feature of reality. The faster you move through space, the slower you move through time. And if that sentence just bounced off you like a tennis ball off a concrete wall, let me try again from a different angle, because I think there's a way to feel this rather than just hear it. Imagine every object in the universe, you, me, every rock on every planet, every wisp of gas in every nebula has a speed limit. Not a speed limit that a traffic cop set. A cosmic one, baked into the structure of reality itself. And every single thing is always traveling at that exact maximum speed, all the time, no exceptions. But, and here's the kicker, that speed is split across two directions. The first direction is through space. That's the regular kind of moving left, right, forward, back, up, down. The second direction is through time. And your total speed, space speed plus time speed, always adds up to the same constant maximum. When you're sitting perfectly still in your living room, barely moving through space at all, almost all of your cosmic speed budget is being spent on time. You're rocketing into the future at full throttle. Every second you sit there, you're aging at the maximum possible rate, traveling through time as fast as the universe will allow. Now start moving through space. Drive your car. Fly on a plane. You're diverting some of your cosmic speed budget from time and pointing it towards space, which means your time speed goes down. You age slightly more slowly. Your watch ticks slightly more slowly than the watch of someone sitting still. The trade-off is so minute at everyday speeds that you'll never feel it. But push that speed toward the speed of light. Put yourself on a spacecraft flying at 99% of light speed, and the trade-off becomes dramatic. You're spending almost your entire speed budget on space, which means almost nothing is left for time. Your watch barely moves. Your heartbeat slows to a crawl. You barely age. And when you come back to Earth, after what felt to you like a few months, years might have passed. Maybe decades. Maybe more. This is called time dilation. It sounds like science fiction. It is science fact. But okay, I know what you're thinking. Because I would be thinking the same thing. Great story, very cinematic, very interstellar. But what does this have to do with my actual life? Today, right now. I'm not planning on getting into a relativistic spacecraft anytime soon. I drive a 2019 Honda Accord, and my biggest speed-related concern is whether I can make the left turn arrow before it goes yellow. I'm glad you brought that up. Here's where things get genuinely wild. Pull out your phone. Open whatever map app you use. Watch that little blue dot appear your precise location to within about 10 to 30 feet, in real time, anywhere on Earth. That little blue dot is not magic. It works because your phone is in constant communication with a network of GPS satellites orbiting the Earth at roughly 8,000 miles per hour. Those satellites are equipped with extremely precise atomic clocks so accurate they'd lose less than a second over 30 million years. Here's the problem. Those satellites are moving fast, very fast. And as we just established, fast movement through space means slower movement through time. The clocks on those satellites, because of their speed, tick slightly more slowly than clocks on the surface of the Earth. On top of that, those satellites are far from Earth, about 12,000 miles up, which means they're in a weaker gravitational field than we are on the surface. And gravity, as we'll get to in a little while, also affects time. Weaker gravity means time actually moves slightly faster up there compared to down here. When you add both effects together, the clocks in GPS satellites run fast by about 38 microseconds every single day. 38 millionths of a second. That sounds like nothing. But light travels about 7 miles in a single microsecond. 38 microseconds of accumulated error per day means roughly 280 miles of position error per day. If the engineers who built the GPS system had said, relativity is just theoretical physics, it doesn't apply to our satellites, your map app would be off by more than the distance from Chicago to St. Louis, every single day. The GPS engineers did not say that. They corrected for it. They plugged in Einstein's equations, the ones that describe how speed and gravity warp time, and they adjusted the satellite clocks accordingly. Your navigation works because time dilation is real, because the equations that describe it are correct, and because someone had the wisdom to take them seriously. The next time you drive somewhere you've never been before and make it without getting lost, thank Einstein. Specifically, thank the part of Einstein that told us time is not the same everywhere. that it bends and stretches based on where you are and how fast you're moving. This is not philosophy. This is engineering. This is how the world works. But now we're ready for the next layer. Because speed and GPS satellites are just the beginning. The real depth charge hasn't gone off yet. Let me ask you something that sounds even more basic than the question I started with. Why does anything fall? You drop your phone, it falls. Why? Gravity, obviously. Gravity pulls it down. But what is gravity? What's actually happening when an object falls? The textbook answer you probably learned in school goes something like this. Massive objects attract each other. The Earth is very massive, so it pulls things toward it. The bigger the mass, the stronger the pull. It's like an invisible rope connecting everything to everything else, with the strength of the rope proportional to mass and distance. Newton gave us this picture. He even gave us the equation for calculating exactly how strong that rope is. And again, it works incredibly well for everyday purposes. We used Newton's gravity to send Voyager 1 past the outer planets with extraordinary precision. The equations hold up beautifully at the scales we normally deal with. But Newton himself admitted something remarkable. He could calculate how gravity behaves. He had no idea what it actually was. In his own words, he refused to feign hypotheses about the mechanism. He just described the pattern and left the why unanswered. The why took another 200 years. And the answer is so strange that I want you to actually brace yourself for a second. Gravity isn't a force. There is no invisible rope. No hand reaching down from the earth to grab your phone. That's not what's happening at all. What's happening is this. Think back to the fabric we've been building spacetime, the unified material that combines space and time into a single four-dimensional structure. I know that sounds abstract, so here's the most useful picture I can give you. Imagine a large, flat sheet stretched out like a bed sheet held taut at the corners. Now, take a heavy bowling ball and set it in the middle of that sheet. What happens? The sheet dips, curves. There's a depression, a bowl shape, spreading out from the bowling ball's position. Now roll a marble across the sheet. If you roll it far enough from the bowling ball, it just curves slightly and keeps going. If you roll it close enough, it spirals inward. And if you roll it at exactly the right speed and angle, it goes around and around and around in a circle it orbits. The marble isn't being grabbed. Nobody is pulling it. It's just rolling along the curved surface, following the path that the geometry of the sheet allows. The shape of the sheet is doing the work. The Earth and every massive object in the universe does this to space-time. The mass doesn't reach out and grab things. It warps the local geometry. It curves the fabric. And everything else rocks, photons. Your dropped phone moves through that curved geometry, following the path of least resistance. And here's the part that made Einstein famous, and that makes physicists today still get a little bit of a chill when they think about it. Remember what we said, that everything in the universe is always moving at that same cosmic speed, partly through space and partly through time? That when you're sitting still, you're directing all your speed into the time dimension, rocketing into the future? Gravity curves the time dimension specifically, not just space, time. When you drop your phone, it's not being pulled down. It's following its natural straight-line path through space-time, a path that, because of the Earth's mass, is bent toward the floor. The floor just happens to intercept that path. And here's the beautiful, dizzy-making consequence. The pressure you feel right now, sitting in your chair or wherever you are, the weight, the sense of being pushed into the surface below you, that's not gravity pulling you down. That's the surface of the Earth pushing you up, preventing you from following your natural free-fall path through curved space-time. The astronauts on the International Space Station aren't weightless because there's no gravity up there. Earth's gravity extends all the way to the ISS and beyond. They're weightless because they're in freefall. They're following their natural curved space-time path without anything blocking them. They're doing what everything naturally does. It's the rest of us, stuck on the surface, being constantly interrupted by the ground, who are in the unusual situation. Sit with that for a second. You are not standing still. You are being perpetually blocked from your natural trajectory through curved space-time. The normal state of matter in a gravitational field is to fall. You are always falling. The floor is what's preventing it. Gravity isn't a force that happens to you. It's the shape of time. And you're embedded in it every moment of your life. We're getting close to the deepest part now. And I want to make sure you're still with me. Because what comes next is where this conversation stops being a cool physics lesson and starts being something that might actually change how you see existence. We've established time is not absolute. It's not the same everywhere. It stretches and compresses depending on how fast you're moving and how deep in a gravitational field you are. Space and time are not separate things. They're two aspects of a single unified structure, spacetime, that can be bent, curved, and warped by mass and energy. Gravity is not a force, it's geometry. It's the curvature of time, pulling objects along bent paths. And E equals mc squared, maybe the most famous equation in human history, falls directly out of this. If space and time are interchangeable, then so are matter and energy. That solid, touchable, stubborn lump of matter sitting on your kitchen counter, it's frozen energy. Enormous amounts of it. The c squared in that equation, the speed of light squared, is a conversion factor so gigantic that even a tiny amount of matter contains enough energy to level a city. The sun is shining because mass is converting to energy. Every second, about 4 million tons of the sun's mass becomes pure energy that radiates outward into the solar system. We experience some fraction of that as daylight and warmth. It all traces back to the flexibility of spacetime. But here's the question I've been building toward. The one that makes physicists uncomfortable at dinner parties and keeps certain kinds of minds awake at 3 in the morning. If space and time are the same kind of thing, if you can trade one for the other the way you can trade dollars for euros, then what does that mean for the past? Think about space for a moment. When you walk away from your house, the house doesn't disappear. It stays there. The space that was occupied by your house when you left is still there. It's still a real coordinate, a real location. You could go back to it. Your house is right there, at its place in space, whether you're looking at it or not. Now, if time is the same kind of thing as space, if past and future are directions in space-time just like north and south are directions in space, then what happens to the past when you leave it behind? Maybe nothing. Maybe it stays there. Maybe the moment you were born is still there, at its coordinate in space-time, just as real and just as present as the location of your childhood home. Not gone, not erased, not eliminated. Just somewhere you're not currently pointing your attention at. This idea has a name. Physicists call it the block universe, or block time, or in more technical language, eternalism. The block universe says this: the universe is not a movie playing one frame at a time. It's the entire film, every frame, from the first to the last, existing simultaneously as a single four-dimensional object. The beginning and the end and the middle are all equally real, all equally present, in the sense that they all exist as actual physical features of space-time. The Big Bang is there. The distant future, whatever it holds, is there. The moment your grandparents met, your first day of school, whatever you had for breakfast in 2011 on a random Wednesday, all of it, every single moment, encoded into the structure of space-time and persisting there, unchanged, forever. The only reason it doesn't feel that way, the only reason it feels like the past is gone and the future is unwritten, is that your consciousness is a small, local thing, a tiny searchlight moving along the film strip, illuminating one frame at a time, which creates the sensation of motion, of flow, of narrative. But the film itself is still. The projection of time is something happening inside your head. I know. That's a big statement. Let me be careful with it. Because here's what I am not saying. I am not saying the future is already written in some mystical, fatalistic way that makes your choices meaningless. I am not saying free will is an illusion in the way that sounds depressing. And I am definitely not saying anything supernatural or mystical. I want to be precise about what physics actually says and where it stops. What I am saying is this: the equations of physics, every major framework we have, from Newton to Einstein to quantum mechanics, make no distinction between past and future at the fundamental level. The laws of physics run equally well forward and backward in time. Nothing in the mathematics picks out now as special. Nothing in the equations says, this moment is where the action is. This is the thin sliver of reality that exists, while everything else doesn't. The equations describe the whole block, all at once, uniformly, with no arrow, no preferred direction, no special status for any particular moment. And yet here you are, experiencing an arrow, experiencing flow, experiencing the vivid, pressing, urgent aliveness of right now, this moment, this specific and particular and irreplaceable now. Where does that come from? This is where we hit the wall that even the most brilliant physicists don't have a clean answer for. And I'll be honest with you, because that's the whole point of this channel. The honest answer is we don't fully know, but we have some very interesting clues. One of them is entropy. You've probably heard the word before. It's often described as disorder or chaos. which is technically accurate, but a little misleading in terms of what it actually means for time. Here's a more precise way to think about it. Every physical system tends, over time, to move from a less likely arrangement to a more likely arrangement. That doesn't sound very profound until you think about what it means. Take a bottle of perfume, uncork it in a room. The perfume molecules start in one corner specifically, in the bottle. That's an extremely specific, ordered, unlikely arrangement. Over time, those molecules spread out, drift, wander, and eventually distribute themselves fairly evenly throughout the room. That's a much more likely arrangement. There are vastly more ways for molecules to be spread evenly throughout a room than there are ways for them all to be crammed into one small corner. The second law of thermodynamics says this process only goes one way. The perfume spreads out. It doesn't spontaneously collect itself back into the bottle. Ice melts in warm water. Warm water doesn't spontaneously freeze in a warm room. A wine glass shatters on a tile floor. The shards do not jump back together. This one-wayness, this directionality, this is where the arrow of time comes from, at least physically, not from the laws themselves, which are symmetric in time, but from the initial conditions of the universe. The Big Bang started the universe in an extraordinarily low entropy, highly ordered, extremely unlikely state. And ever since then, entropy has been increasing. The universe has been running downhill from that improbable starting point toward more probable arrangements. And we are entropy processing machines. Our memories are records of past entropy states. Our brains build representations of events that have already happened, because those events left traces, because increasing entropy leaves marks, because effects follow causes, because a smashed wine glass leaves shards and not the other way around. So in some deep sense, the reason you feel like time moves forward, the reason you remember yesterday but not tomorrow, the reason cause seems to precede effect, the reason you experience the vivid asymmetry of past versus future is that you are a child of the Big Bang, living in the long, slow, thermodynamic exhale of an improbably ordered starting point. The river of time is real as an experience, but it's generated inside the block. It's not written into the fundamental laws. It emerges from initial conditions. Now here's the part I find most beautiful and most humbling. Go back to the LP record for a moment. Old school vinyl, the big flat disc. A record contains music. The entire piece, the opening notes, the crescendo, the ending, is encoded into the grooves of the record, all at once, simultaneously. Every moment of the symphony exists in the vinyl at the same time, but you don't experience all of it at once. The only way to turn that encoded information into actual music, into something you can hear and feel and be moved by, is to run a needle along the groove. And the needle reads one moment at a time. It moves through the record in order, forward. The music is not in the needle. The music is in the grooves. But without the needle, there is no music, just patterns in plastic. Physics understands the record beautifully. It can map out every groove with extraordinary precision. It can predict, in principle, what the next note will sound like. What physics cannot fully explain is the needle. The thing that moves through the record and turns grooves into music. The thing that turns coordinates in spacetime into the felt, living, first-person experience of now. That's consciousness. And consciousness is the most mysterious thing in the universe. I want to be very clear. I'm not making a mystical claim here. I'm not saying consciousness is outside physics, or that the mind is magic, or anything like that. I'm saying that within physics, within the most rigorous, most carefully tested framework humans have ever built, the experience of now remains unexplained. Not mysterious in a spiritual way. Mysterious in the hardest, most technically rigorous scientific way. We don't know the mechanism. We have guesses, hypotheses, research programs, but the answer, not yet. What we know is this. You are the needle. Your consciousness, whatever it is, moves through the block, illuminating one frame at a time, turning the static mathematics of space-time into the dynamic, flowing, felt experience of being alive. And that's not a small thing. That's possibly the most extraordinary thing in the universe. So let's pull back. Let's take the wide view, the one that Feynman always insisted on, the view where you hold the whole problem in your head at once, where you don't let any one piece of the puzzle get too comfortable. Here is what we've established tonight. Time is not a river carrying you somewhere. It is a dimension of a larger structure, a direction in a four-dimensional block. And like any direction in space, it is not inherently special. There is no cosmic arrow painted on it pointing toward the future. There is no preferred now. There is no universal clock ticking for everybody. When you move through space, you trade time for distance, and your clock ticks more slowly relative to someone standing still, not metaphorically, not approximately, literally, measurably, verifiably. This effect powers the GPS satellites that let you find your way home. Massive objects, including the Earth beneath your feet, warp space-time. Gravity is not a force, it's the geometry of curved time. You're not pulled down by a rope. Your natural path through space-time points toward the ground, and the ground keeps blocking you. And the past, your past, the history of the universe, every moment that has ever happened might not be gone. It might be as real and as persistent as the space on the other side of your house when you're not looking at it, encoded, static, permanent, a feature of the block. What does any of this mean for how you live? I've been thinking about this a lot, and I want to offer you something not as a physicist, not as a philosopher, but just as someone who has spent a lot of time trying to genuinely think these things through rather than just finding a comfortable answer and stopping. If the past persists, if it's not erased, not obliterated, not lost, but rather fixed into the fabric of space-time at its coordinate, then every moment of genuine connection, of real experience, of actual presence, has a kind of permanence to it. Not the permanence of a photograph, which is just a representation. The permanence of an event, of something that happened and by virtue of having happened is woven into the universe permanently. Every morning you've ever woken up and felt genuinely okay. Every moment you've laughed hard enough that your face hurt. Every conversation where you really said what you meant or really listened to someone who needed it, those didn't evaporate. They're there, in the block. They count. They're part of the structure of what exists. That doesn't mean loss doesn't hurt. It does. The people we love, the moments we miss, the chances we didn't take the pain of those things is completely real. But maybe there's something in knowing that the good moments, the real ones, aren't nothing. They're coordinates. They happened. The universe knows. And meanwhile, the moment you're in right now, whatever it is, wherever you are, whatever's going on in your life, this moment is in the process of becoming permanent. Right now, you are laying down another coordinate, another groove in the record. That's what Feynman was pointing at, I think, when he said in one of his less famous but more personal moments that he found it possible to live without being afraid of death because he'd already had the experience of being alive. The living was the thing. The having experienced was already an achievement that nothing could take away. The universe doesn't have a mechanism for erasing what has been. It has no delete key. Once something has happened, it is, in some deep physical sense, always having happened. It occupies its place in the block forever, which means that what matters, genuinely matters, is which coordinates you're creating, what you're putting into the block. Whether the groove your needle is cutting right now is one you'll be glad existed. There's one more thing I want to say before I let you go, and it's about the strangest implication of everything we've talked about tonight. If your experience of time flowing the river, the movement, the sense of being swept forward is generated by your consciousness moving through a static block rather than by time itself actually flowing, then what you call now is not a feature of the universe. It's a feature of you. The universe does not have a now. The universe has coordinates. It has locations in four-dimensional space-time. It has the block, the whole thing, all at once. You are the thing that turns coordinates into now. Your experience, first person, felt, vivid, irreducible, is the mechanism by which the static becomes dynamic, by which the mathematics becomes music. That's not a small role to play. That might be the most important role in the universe, or at least the most interesting one. So the next time you're sitting somewhere, maybe early morning, coffee in hand, nothing demanding your attention yet, and you notice time passing, and it feels a little melancholy, a little beautiful, a little strange. Remember this. You're not watching time flow. There's no flow. You are the flowing. You are the needle on the record. You are the searchlight moving across the block. And the light you're shining, the consciousness that turns a coordinate in space-time into this moment, your moment, the only moment you'll ever have direct access to that light, is the rarest thing in the known universe. Rarer than gold. Rarer than any element on the periodic table. Rarer, arguably, than anything we've ever measured or named. Don't waste it looking at the clock. Look at what's actually here. Thank you for spending part of your block with Feynman's path tonight. If this kind of conversation where physics and philosophy crash into each other and neither one walks away clean is your thing, we've got a lot more coming. Subscribe if you haven't. Hit the notification bell if you want to actually see when we post, because YouTube's algorithm is doing its own version of warping spacetime and nobody fully understands it. Next time, we're going after another one of those questions that sounds absurdly simple right up until it completely isn't. One that Feynman himself said bothered him more than almost anything in physics. We'll see you there.